In September 2023, the James Webb Space Telescope detected something in the atmosphere of a planet 120 light-years away that had no business being there. A molecule. One that, on Earth, is produced almost exclusively by living things. The scientists who found it went quiet for 6 months before saying anything publicly. And when they finally did speak, they chose their words with surgical precision. Not life. Not inhabited. They said potential biosignature. They said requires further investigation. Language so careful it felt like a legal document written by people who knew exactly what they were saying and were terrified to say it. What they found was a chemical whisper. So faint it barely cleared the noise floor of the most powerful space telescope humanity has ever constructed. But it was there. Faint. Persistent. Real. And if they are right, if the signal is genuine and the interpretation holds, then we have already detected the first evidence of life beyond Earth. We just haven't said so yet. What comes next will change how you understand the sky above you every night. It will change what silence means. It will change what loneliness means. And it may change, in ways that are difficult to fully prepare for, what it means to be human on a planet that is no longer the only living world we know of. Because this is not a story about a planet we found. This is a story about a planet that may have been full of life for longer than our species has existed. A world orbiting a star we can locate with the right telescope, close enough that light from its surface is already inside our solar system right now, arriving as you listen to this. The question is not whether we have found it. The question is what finding it actually means. And the answer, when you follow the physics and the philosophy all the way to the end, is something that science has never had to confront before. We're about to confront it together. If the kind of journey that reshapes how you see the universe is what you came here for, do me a small favour, hit that like button and subscribe. It genuinely helps this channel reach the people who need these conversations most. Get comfortable. Turn the lights down. To understand what James Webb found, you first need to understand what James Webb is. Not just as an engineering achievement, though it is the greatest engineering achievement of the 21st century so far, full stop. You need to understand it as a fundamentally new kind of eye. An eye that sees things the human retina cannot. An eye calibrated not for the visible universe, but for the invisible one. The James Webb Space Telescope launched on Christmas Day, 2021, after more than 30 years of development, $14 billion in funding, and multiple near cancellations that could have ended it before it ever left the ground. It folded into a rocket like an origami crane, a 6.5-meter gold-plated mirror composed of 18 hexagonal segments, a sun shield the size of a tennis court, and an instrument package capable of detecting the heat signature of a single bee at the distance of the Moon. It travelled to a point in space called Lagrange Point 2, approximately 1 million miles from Earth in the direction directly away from the Sun. This is not an orbit in any conventional sense. It is a gravitational sweet spot where the combined pull of Earth and the Sun allows an object to maintain a fixed position relative to both. Webb sits there, cold and still, bathed in perpetual shadow from the sun shield, its instruments cooled to temperatures approaching negative 270 degrees Celsius, nearly the coldest point achievable in the natural universe. It had to be this cold, because what it was designed to see is heat. Specifically, the infrared glow of ancient light, photons that left their sources billions of years ago, stretched by the expansion of the universe from visible wavelengths to infrared during their journey across the cosmos. Webb was built to catch those ancient photons, to read their wavelengths, to decode their histories, and in doing so to see further back in time than any instrument ever built. What nobody expected, or at least what nobody said publicly, was how quickly it would also transform our understanding of planets we can barely see. Because Webb does not just see far, it sees through. When a planet passes in front of its host star, a tiny fraction of that star's light filters through the planet's atmosphere on its way to us. Different molecules in that atmosphere absorb different wavelengths of light. Oxygen absorbs some, methane absorbs others, water vapour leaves its own specific fingerprint. Carbon dioxide has a signature so distinctive that Webb can identify it in an atmosphere 40 light-years away. This technique is called transmission spectroscopy. It is how we read the chemical composition of alien skies without ever visiting them. It is how we take the equivalent of a blood test on a planet from a distance of trillions of miles. And in 2023, when Webb turned this technique on a planet called K2-18b, the blood test came back with something that made the laboratory go silent. K2-18b was not supposed to be interesting. It was discovered in 2015 by the Kepler Space Telescope during its K2 extended mission, a period when Kepler was running on damaged reaction wheels and limping through the sky, surveying stars in a desperate attempt to justify its continued operation before the fuel ran out. It found K2-18b the way a fisherman nets a small, unremarkable fish, incidentally in passing, almost by accident. The planet is approximately 2.6 times the radius of Earth and 8.6 times Earth's mass. It sits in the habitable zone of its host star, a red dwarf called K2-18, located 120 light-years away in the constellation Leo. At that distance, you cannot see K2-18 with the naked eye. But it is there, burning red and dim, smaller and cooler than our Sun, and it has been burning for billions of years. K2-18b was classified initially as a super-Earth, a rocky planet larger than ours but potentially solid, potentially capable of holding an atmosphere, potentially capable of something. But the early data was frustratingly ambiguous. It could be a rock wrapped in hydrogen. It could be a water world with no solid surface. It could be something in between, a class of planet that doesn't exist in our solar system, for which we had no good models, no clear template, no easy framework for understanding. Planetary scientists call these objects Hycean worlds. Hycean, a portmanteau of hydrogen and ocean. The idea is this. Imagine a planet slightly larger than Earth, with a deep global ocean of liquid water beneath a thick hydrogen-rich atmosphere. No continents, no dry land anywhere on the surface. Just water stretching from horizon to horizon, beneath a sky that is not blue but hazy and thick and opaque. A world that looks nothing like Earth from the inside, but which might, from a thermodynamic standpoint, provide conditions where life could arise. This is what researchers at Cambridge University proposed K2-18b might be. In 2021, before Webb launched, they published a theoretical paper arguing that Hycean worlds like K2-18b should be considered high-priority targets in the search for biosignatures, detectable chemical signs of biological processes, because their large size and hydrogen atmospheres would make those signatures far easier to detect than the thin, nitrogen-oxygen atmosphere of a world like ours. It was a theoretical argument made in advance of the data, a prediction, and in science, making a prediction and then having the universe confirm it is a rare and sacred thing. Webb confirmed it. In September 2023, a team led by astronomer Niku Madhusudan at Cambridge's Institute of Astronomy published results in the astrophysical journal Letters from Webb's transmission spectroscopy analysis of K2-18b. The data showed, with high statistical confidence, the presence of carbon dioxide and methane in the planet's atmosphere. This combination is consistent with a Hycean world, a global ocean beneath a hydrogen-rich sky. But that was not what stopped the room. What stopped the room was the tentative, extremely tentative, the researchers were careful to emphasize tentative, detection of a second molecule, dimethyl sulfide, DMS for short, a molecule with a very simple structure, a sulfur atom bonded to two methyl groups, unremarkable by the standards of organic chemistry, almost boring. Except for one thing, on Earth, dimethyl sulfide is produced almost exclusively by living organisms, specifically by phytoplankton, the microscopic marine algae that drift through the sunlit surface layers of the world's oceans in quantities almost beyond counting. When phytoplankton metabolize certain compounds, one of the byproducts they release into the atmosphere above them is dimethyl sulfide. It drifts upward, it scatters into the atmosphere, it creates a chemical signature in the spectrum of light passing through the air above the ocean. It is a biological exhaust, a metabolic fingerprint, the chemical equivalent of smoke rising from a fire, and Webb detected it, faintly, tentatively, with caveats and error bars and qualifications that filled pages of the published paper. But it detected it. The team was careful, almost painfully careful, to say this was a tentative detection, that the signal was weak, that alternative abiotic sources of DMS cannot yet be ruled out, that additional observations would be needed to confirm or refute the finding. They were not claiming they had found life. They were claiming they had found a signal consistent with life, in a context where life is theoretically possible. That is the most cautious possible language scientists can use to describe what they found, and what they found was a potential biosignature in the atmosphere of a planet, sitting in the habitable zone of a stable star 120 light-years away, in an ocean world that may be teeming with the alien equivalent of algae. Sit with that for a moment. There is a philosophical problem embedded in the detection of a single molecule in an alien atmosphere that science has not yet fully worked out how to handle. It is not a problem of data. Data we can get more of. Webb will continue observing K2-18b. Other telescopes will follow. Future instruments will refine the measurements, reduce the error bars, confirm or deny the DMS signal with increasing certainty over the coming years and decades. The problem is what to do with the knowledge while the confirmation is still pending. Because here is the situation we are in right now, as you listen to this in this moment. We have detected a signal on another world that, on our world, is only produced by living things. We cannot yet confirm it with absolute certainty. We cannot yet rule out alternative explanations with absolute certainty. We exist in a zone of profound ambiguity, holding a piece of evidence that could be the most important discovery in human history, or could turn out to be instrumental noise, or some exotic abiotic chemistry we don't yet understand, and we have to live in that zone. We have to think about it and talk about it and sit with it, while the universe takes its time revealing the answer. This is not a comfortable place to exist. Consider the history of moments like this one. In 1996, a team of NASA scientists announced they had found possible traces of ancient microbial life inside a Martian meteorite, a rock blasted off the surface of Mars by an asteroid impact billions of years ago and eventually recovered from Antarctica. The announcement made front pages around the world. President Clinton gave a statement about it from the White House lawn. And then, slowly, over the following years and decades, the evidence was picked apart, alternative explanations were proposed, and the scientific community moved from cautious excitement to cautious skepticism. The meteorite has never been fully vindicated and never been fully debunked. It sits in the Smithsonian Institution in a temperature-controlled case, still studied, still debated, still ambiguous after nearly 30 years. The DMS detection on K2-18b is different. It is more rigorous. It was made by a space telescope specifically designed for this kind of measurement, using a technique that had been validated on dozens of other planetary atmospheres, analysed by teams who were hyper-aware of the pressure they were under and the care they needed to take. The statistical significance of the detection, while not yet at the threshold scientists typically require for a confirmed discovery, is real. The signal is above noise. The molecule appears to be there, but appears to be is not the same as is. And in science, that distinction matters enormously, even when it is agonizing to maintain it. So here is what we know. We know K2-18b exists. We know it is in the habitable zone. We know it has an atmosphere containing carbon dioxide and methane in proportions consistent with a world that has a liquid ocean. We know a signal consistent with dimethyl sulfide appears to be present in that atmosphere. We know that on Earth, dimethyl sulfide at atmospheric scales is a product of biological activity. We do not know, yet, whether K2-18b's DMS is also biological in origin. But we need to talk about what happens if it is, because the implications do not scale linearly with the evidence. The implications are not just bigger than what we found. They are a different category of thing entirely. They are not a larger version of ordinary scientific discovery. They are the end of one era of human history and the beginning of another. To understand why, you need to understand what finding life at K2-18b would actually mean. Not just scientifically, but cosmologically. Not just for astronomy, but for everything. Let us assume the signal is real, not because we have confirmation, we don't yet, but because following the assumption to its conclusion is how we begin to understand what we are actually dealing with. Assume that K2-18b has a global ocean. Assume that ocean is warm enough and chemically rich enough for life to have arisen at some point in its history. Assume that phytoplankton-like organisms, or something so unlike phytoplankton that we would not recognize them as organisms at all, but which perform the same thermodynamic function, drift through that ocean, metabolizing, reproducing, and exhaling dimethyl sulfide into the sky above them, just as our phytoplankton have done for hundreds of millions of years. Assume K2-18b is alive. What does that mean? The first thing it means is that we are not alone. This sounds simple. It sounds like something you've already heard, already processed, already prepared yourself for emotionally. But I want to push on that preparation for a moment, because I think most people, when they imagine the confirmation of extraterrestrial life, imagine something dramatically different from phytoplankton. They imagine signals, spacecraft, structures. They imagine contact in some meaningful communicative sense, the alien equivalent of a handshake, or at minimum a detectable technological footprint, something that implies intention and intelligence. A planet full of microscopic marine algae is not that. It is something both more and less than that simultaneously. It is less, in the sense that phytoplankton do not build radio telescopes. They do not wonder about us. They do not know they are being watched from 120 light-years away by a golden mirror unfolding in the cold between stars. They simply drift, they metabolize, they divide. They have no concept of the universe they inhabit or the attention they have attracted. But it is more in a sense that takes time to grasp. Because the discovery of any life, even microbial, even single-celled, even utterly mindless, at K2-18b would tell us something that no technological contact ever could. It would tell us that life is not a cosmic accident. It is a cosmic pattern. Here is the statistical logic of that statement. We currently have exactly one data point on the emergence of life, Earth. From that single data point, we cannot determine whether life is common or extraordinarily rare. We cannot know if Earth is the only living world in the galaxy, or one of billions. One data point tells us only that it happened once. It says nothing about frequency. A second data point, K2-18b, alive, changes everything. In statistics, one occurrence of a rare event tells you very little. Two independent occurrences separated by 120 light-years in a galaxy, 100,000 light-years across, tell you it is not rare at all. It tells you it is probably common. It might tell you it is essentially inevitable wherever the conditions are right. That the chemistry of life, given liquid water and an energy source and time, finds a way to organize itself almost automatically, not every time, not guaranteed. But often enough that across a galaxy of hundreds of billions of stars, life is not the exception. Life is the rule. Consider what that means for the number of planets in the Milky Way that are alive right now. Current estimates based on Kepler data suggest that roughly 1 in 5 Sun-like stars hosts a rocky planet in the habitable zone. Expand that to include red dwarfs, which outnumber Sun-like stars by roughly 2 to 1, and factor in Hycean-class worlds, and the number of potentially habitable planets in our galaxy alone may exceed tens of billions. If life arises whenever conditions permit, if the discovery of K2-18b tells us that life is not a 1,000,000 to 1 shot but closer to a 1 in 10 shot, then the galaxy contains not hundreds of living worlds, but billions. Billions of oceans, billions of skies, billions of biospheres quietly going about the business of metabolizing and reproducing, exhaling their chemical fingerprints into their atmospheres, oblivious to the cosmos around them. And we have been alone with this knowledge, the knowledge that those worlds might exist, that the math says they should exist, for decades. But knowledge and certainty are different things. Suspicion and evidence are different things. K2-18b, if its signal holds, would give us the evidence. For the first time in the history of our species, we would have confirmation that we are not cosmically unique, not just philosophically probable, confirmed. That confirmation does not come with a ceremony. It comes with a spectroscopic graph on a scientific paper. 17 atoms arranged in a specific configuration, detected as an absorption feature in the infrared spectrum of a planet 120 light-years away. And yet it would be the most significant moment in human history since the invention of language. There is a dimension to the K2-18b discovery that almost nobody talks about when they discuss it in terms of life and biosignatures and the search for extraterrestrial biology. It is the dimension of time, and it changes the story in ways that are, depending on your temperament, either beautiful or deeply unsettling. K218b is 120 light-years away. That number is so familiar now, so embedded in the discussion of this planet that it has stopped feeling strange. But 120 light-years is not just a distance, it is also a duration. It is a gap in time that separates the event from the observation. When Webb collected the light from K218b's atmosphere and measured the spectral fingerprint of its molecules, it was not collecting information about K218b as it exists right now. It was collecting information about K218b as it existed 120 years ago. The light that tells us K218b may be alive left that planet in the year 1903. It crossed 120 light-years of empty space, passed through the infrared detectors of the James Webb Space Telescope, and we read it in 2023. What is happening on K2-18b right now, in this moment, as you listen to this, is something we will not know for another 120 years. And what we know about K2-18b right now, in this moment, is what was happening there when the Wright brothers were making their first flights at Kitty Hawk. This is the fundamental strangeness of astronomical observation. We do not see the universe as it is, we see it as it was. Every photon that reaches our telescopes is a message from the past. The further away the source, the older the message. The stars you see on a clear night are showing you light that left them decades, centuries, thousands of years ago. The Andromeda Galaxy, visible as a faint smudge to the naked eye, shows you light that left it 2.5 million years ago. Light that began its journey before our species existed. The universe we observe is not the universe that exists. It is the universe that existed, displayed on a time-delayed screen of astronomical proportions. For most of human history, this fact was interesting but not personally relevant. The stars we observed were not places we thought of as inhabited. Their temporal displacement was an abstract curiosity, something physicists noted in equations and philosophers occasionally meditated on, but not something that pressed against the bones of ordinary human experience. K2-18b changes that, because K2-18b may be inhabited. And if it is, if those phytoplankton-like organisms are really out there, drifting in an alien ocean, then the light delay is not an abstraction. It is a hard, concrete, slightly haunting fact about what we are and are not able to know. Think about it this way. We detected what may be biological activity on K2-18b using light that left that planet 120 years ago. We are reading the life signs of a world 120 years in its past. Whatever those organisms were doing in 1903, dividing, metabolizing, that is what we have evidence of. That is the moment we're observing. What those organisms are doing now, in the year you're listening to this, we cannot know. The light carrying that information is still en route. It will not arrive for another 120 years. Our great-great-grandchildren, if Webb or some successor instrument is still in operation, will be the first humans to see what K2-18b looks like in this moment. And there is a version of this story that is even more disquieting. What if, between 1903 and now, something changed on K2-18b? Not catastrophically, not necessarily. But oceanic ecosystems are dynamic. Phytoplankton populations on Earth fluctuate enormously with temperature. Nutrient availability and the chemical composition of the water. A shift in K2-18's output, a change in the chemistry of K2-18b's ocean, a volcanic event on the seafloor. Any of these could have expanded or contracted the biological signature we observe, or eliminated it entirely. What if K2-18b was alive 120 years ago and is not alive now? Not through any dramatic extinction, just through a natural fluctuation, a temporary collapse of the biosphere, a biological winter that the ecosystem is still recovering from. We would have no way to know. The light telling us it happened has not arrived yet. We could be celebrating the detection of life on a world that is currently in this moment as dead as the moon. Or, and this is the inversion of that thought, and it is no less strange, what if K2-18b was only marginally alive in 1903 and has since exploded into biological richness? What if the faint DMS signal we detected was the beginning of something, a young biosphere still finding its feet, that has since grown into a planet teeming with life more complex than anything we have yet measured? We cannot know. The information is locked inside light that is still crossing the void between stars, 120 years away from delivering its message. We are holding a photograph of a world, taken in 1903, and asking what it looks like today. This is what it means to do science across interstellar distances. Not just the science of detection and measurement and statistical significance. The science of accepting radical uncertainty about the present, because the only information available to us is ancient. The science of learning to live with the knowledge that the universe we observe and the universe that exists are not the same universe, and learning to hold that gap, to sit inside it, without letting it collapse into despair on one end or false certainty on the other. We did not arrive at K218b by accident, and to understand how significant this moment is, you need to understand how long humanity has been walking toward it. The search for another Earth, another world where life might exist, where the conditions for biology are met, where the universe has done what it did here, is one of the oldest and most persistent drives in human intellectual history. It predates telescopes. It predates modern science. It is embedded in the philosophy of ancient Greece, in the theology of medieval scholars, in the poetry of Enlightenment thinkers who looked up at a sky full of stars and asked, with increasing urgency, whether any of them had someone looking back. The philosopher Epicurus, writing in the 3rd century BCE, argued that it was irrational to suppose that the Earth was the only inhabited world. His reasoning was not empirical. He had no data, no telescope, no spectroscope. It was philosophical, rooted in the logic of probability and the principles of atomism. If matter arranges itself into worlds here, it must arrange itself into worlds elsewhere. 2,000 years later, Giordano Bruno was burned at the stake in Rome in 1600, in part for insisting that the stars were other suns, orbited by other worlds, and some of which might harbour other living beings. Bruno was not a careful scientist. He was a philosopher, a mystic, sometimes an occultist, whose ideas were as much theological as astronomical. But his intuition was correct in ways that the Church found unacceptable. The cosmos is vast, and we are probably not its only inhabitants. It took until the 20th century for that intuition to acquire the tools it needed to test itself. The first exoplanet, a planet orbiting a star other than our Sun, was confirmed in 1992 when astronomers detected 2 planets orbiting a pulsar 2,300 light-years away. It was a strange, ironic first discovery. Planets orbiting a dead star, bathed in lethal radiation, about as inhospitable as anything in the galaxy. But they were there. Planets existed beyond our solar system. The hypothesis was confirmed. 3 years later, in 1995, the first exoplanet orbiting a Sun-like star was confirmed. 51 Pegasi b, a gas giant orbiting so close to its host star that its year lasted only 4 days, upended our models of planetary formation and announced, definitively, that the galaxy was full of planetary systems arranged in ways we had not anticipated. What followed was a revolution in astronomical observation that has not yet stopped accelerating. The Kepler Space Telescope, launched in 2009, surveyed more than 150,000 stars and confirmed over 2,600 planets. It established with statistical confidence that planets are not rare. They are essentially universal. Most stars have them. Many systems have multiple planets. Rocky planets in habitable zones exist in enormous numbers. The Transiting Exoplanet Survey satellite, T, launched in 2018, extended Kepler's survey across nearly the entire sky, identifying thousands more candidate worlds. Ground-based telescopes added radial velocity measurements, transit timing variations, direct imaging, every technique available, to build the richest catalogue of exoplanets in human history. By the time James Webb launched in 2021, we knew of over 5,000 confirmed exoplanets, 5,000 worlds beyond our solar system, ranging from gas giants larger than Jupiter to super-Earths smaller than Neptune, from planets orbiting so close to their stars they have magma oceans on their surfaces, to planets in the habitable zones of stable stars where liquid water could persist for billions of years. We had, in other words, found the candidates, the places where life might exist, the worlds whose atmospheres we wanted to read. What we had not yet built was the instrument capable of reading them. That was Webb's purpose, not just to see farther, to see deeper, to take the exoplanet sensors built by Kepler and TESS and begin the chemical analysis, to point at these worlds and ask not just are you there, but what are you made of and is anyone home? The first generation of that question has now been answered for K218b. The answer is maybe. That maybe is the most consequential maybe in the history of science. Not because it is certain, because it is the first time the instrument has been good enough to ask the question seriously, not philosophically, not theoretically, empirically, with data, with error bars, with peer review and publication, and the full machinery of scientific verification. We have been walking toward this question for 2,300 years. From Epicurus to Giordano Bruno to Kepler to Webb, and now we are standing at its edge. There is something important about K218, the star at the centre of this story, that deserves its own chapter, because it changes the implications of a living K218b in ways that are not immediately obvious, and that have profound consequences for how we think about life in the universe. K2-18 is a red dwarf, M-class, small, cool, dim. It burns at roughly 3,400 Kelvin, nearly 2,000 degrees cooler than our Sun. It produces about 3% of the luminous energy our Sun does. It is, by the standards of stellar physics, a very ordinary, very unremarkable star. The kind of star that barely shows up in the night sky catalogue. The kind of star that, before the exoplanet revolution, astronomers largely ignored when searching for signs of life. The reason they ignored it is the flare problem. Red dwarfs are active. Young red dwarfs in particular are prone to violent stellar flares, explosions of electromagnetic radiation, and charged particles from the stellar surface that can dwarf anything our Sun produces. A major red dwarf flare can briefly increase the star's luminosity by a factor of 10 or more. It can strip the atmosphere from an orbiting planet, bombard its surface with UV radiation powerful enough to destroy organic molecules, and render conditions for life not just difficult but actively hostile. For this reason, many astrobiologists in the early 21st century argued that red dwarf planets, despite being statistically the most common type of habitable zone candidate, were unlikely to harbour life. The flares were simply too devastating. But the argument was never settled, and K218b complicates it significantly. K218 is an older red dwarf. Stellar activity decreases substantially with age in M-class stars. By the time a red dwarf has burned for several billion years, its flare rate has dropped dramatically. K218 appears to be in this more settled phase. Less active, more stable, better suited to providing a consistent energy environment for whatever processes might be unfolding on its planet. Moreover, Hycean worlds have a built-in defense against stellar flares that rocky planets lack. A global deep ocean is an extraordinarily effective radiation shield. The surface of the ocean absorbs stellar UV and X-ray flux. The upper atmosphere bears the brunt of charged particle bombardment. But beneath the ocean surface, below even a few meters of water, the radiation environment drops to levels that life on Earth has been surviving without difficulty for billions of years. The phytoplankton-like organisms we imagine drifting through K218b's ocean would not need to survive the full fury of stellar flares. They would need only to survive the attenuated version that filters through hundreds or thousands of meters of water above them. Life on Earth evolved in oceans under similar constraints. The UV radiation from a young active sun was significantly more intense 3 to 4 billion years ago than it is today. Life persisted by developing beneath the ocean's surface, shielded by water, evolving the biochemical tools to cope with an environment that was, by later standards, hostile. If K218b's ocean is deep enough, and Hycean world models suggest it may be thousands of kilometers deep, then life there would have been shielded from the stellar environment above it for its entire evolutionary history. It would never have needed to develop radiation resistance because radiation would simply not have been its problem. This matters because it means K2-18, for all the initial objections to red dwarfs as hosts for living worlds, may actually be a reasonable parent star for the biosphere we are tentatively detecting. The life we may have found is not living on an open, irradiated plain. It is living in an ocean so deep that the star above it is barely visible. A dim red glow filtering down through miles of water, providing just enough energy for photosynthesis-like processes to extract from light that is already attenuated, already transformed by its journey through atmosphere and sea. Life finding a way, as it always seems to on Earth, in the least obvious corners of the environment, and red dwarfs are by far the most common type of star in the galaxy. They represent approximately 70% of all stellar objects in the Milky Way. If red dwarf planets can support life, if the flare objection is wrong or overstated or solvable by deep ocean shielding, then the number of living worlds in our galaxy is not tens of billions, it is hundreds of billions. The universe, if K218b is alive, is saturated with life. There is a specific kind of institutional silence that settles over a scientific community when it has found something it cannot yet prove but cannot ignore. It is not the silence of ignorance, it is the silence of precision, the careful, disciplined suppression of implication that science demands when evidence is present but confirmation is pending. The researchers who published the K218b DMS paper knew exactly what they had potentially found. They are not naive. They understand biosignatures. They understand what dimethyl sulfide means on a planet with a liquid ocean in a habitable zone. They understand that they may be sitting on the most consequential data set in scientific history, and they said, tentative detection, requires further study, cannot rule out abiotic sources. This is not cowardice. This is the correct response. Science moves slowly precisely because moving slowly is how it avoids catastrophic errors. The history of premature announcements of extraterrestrial life is not a proud one. The Martian meteorite in 1996, the phosphine detection on Venus in 2020 that subsequently generated intense methodological debate, the 1967 detection of what appeared to be an artificial radio signal, nicknamed Little Green Men by the scientist who found it before it was explained as a rapidly rotating neutron star. Science has been here before. It knows the danger of announcement without confirmation. It knows what happens to careers, to institutions, to the public understanding of science when a claim of this magnitude is made prematurely. So the language is careful, measured, surgical, but read between the lines. The Cambridge team chose to publish. They did not sit on the data. They did not wait for the DMS signal to either disappear or strengthen before going public. They published a peer-reviewed paper in one of the most respected astrophysics journals in the world, describing a tentative detection of a biosignature molecule in the atmosphere of a Hycean world. That is a choice. It is deliberate, consequential, carefully considered choice. Publishing means saying, this is real enough to talk about. This is real enough to invite scrutiny. This is real enough that the scientific community needs to know it exists, and needs to begin designing the follow-up observations that will determine whether it survives. The decision to publish at the tentative stage rather than waiting tells you something about the signal itself. It was not so marginal that it could be dismissed internally. It was not noise that got accidentally included in the data set. It was something that multiple researchers at multiple institutions looked at and said, this needs to be out there. They cannot say, we found life, but they published. And in the language of science, that is as close as institutional caution allows to saying, we think we found something. Here is a question that has not been asked clearly enough in the public conversation about K218b. If it is alive, if the phytoplankton are real, if the DMS is biological, in what sense is it a second Earth? The popular framing of this discovery uses words like New Earth and Earth 2.0 in headlines, and that framing is understandable. It is trying to convey something true, that this is a world where the conditions for life as we understand it have been met, where biology has taken root, where a planet is not a dead rock but a living system. But K218b is not Earth. It may not even be close to Earth in any experiential sense. And understanding how different it is, how alien it is, matters for understanding what the discovery of life there would actually mean. Start with the sky. K218b has no surface you could stand on. It is an ocean world covered entirely by water, with no land anywhere. The clouds above that ocean, if they exist, would be unlike any Earth cloud, thicker, higher, denser, formed from water vapour in a hydrogen atmosphere rather than a nitrogen-oxygen one. The air would be unbreathable. The pressure at any altitude that might be comfortable for a human body would not be compatible with human biology. Now look up from that imaginary vantage point on the ocean's surface. The star above you, K218, is a dim red point of light. Not the brilliant golden white disk we know as the sun. a dark, smouldering ember, roughly 1/4 the angular size of our sun in our sky, casting a reddish, ruddy light across the water. The kind of light that, on Earth, you only see during a deep sunset, when the atmosphere has filtered out the blue and left only the long red wavelengths. That red light is what the organisms of K2-18b evolved under. Their photosynthesis analogue, if they have one, would be calibrated for red photons. Their biochemistry would be built around chemistry that functions in hydrogen-rich water rather than the oxygen-dominated chemistry of Earth life. They might not use chlorophyll, they might not use DNA as we know it. They might use a different molecular alphabet entirely, a genetic system based on different base pairs, different amino acids, different molecular machinery, shaped by billions of years of evolution in a chemical environment that never intersected with ours. They would be life, unambiguously provably life, self-replicating, metabolizing, adapting to their environment, exhaling their metabolic products into the sky above them. But they would be as unlike Earth life as anything we can imagine, not in the way that an octopus is unlike a human. In the way that biology is implemented in hydrogen-rich alien ocean is unlike biology as implemented on a rocky planet with an oxygen atmosphere. They would be the second discovered example of life in the universe. They would prove that life is not a singular cosmic accident. They would carry the same profound implications for the universality of biology that a second data point always carries in science. And they would be completely, utterly, incomprehensibly foreign. This is what a second Earth actually looks like. Not a world with mountains and rivers and a blue sky. A world that is so unlike ours that the only thing it shares with Earth, the only thing, is the fact that something metabolizes within it. That chemistry has organized itself into self-replicating patterns, that in some fundamental thermodynamic sense, it is alive. That is enough. That is more than enough. That is everything. But let us be clear about what we have found, if we have found it. Not a home, not a destination, not a mirror of ourselves, a proof, a demonstration, a confirmation that the universe produces life not as a singular anomaly, but as a pattern, that wherever the conditions are right, the chemistry assembles, and something that wants to persist, persists. Webb is not finished with K2-18b, it has barely begun. The 2023 paper was based on a limited number of transit observations, moments when K2-18b passed in front of its host star, allowing the telescope to collect spectroscopic data from the filtered starlight. Each transit observation adds more data, more statistical confidence, more resolution to the spectral fingerprint we are building of this world's atmosphere. The telescope will observe more transits. Other ground-based and space-based instruments will add complementary data. The next generation of telescopes, the extremely large telescope currently under construction in Chile, the planned Habitable Worlds Observatory, future space missions specifically designed for atmospheric biosignature detection, will be able to observe K2-18b with sensitivity far exceeding what Webb can achieve. The DMS signal will either strengthen or disappear. The error bars will shrink. The alternative explanations will either be ruled out or confirmed. Science will do what science does, slowly, methodically, stubbornly accumulate certainty. The timeline for that certainty is not weeks or months. It is probably years, possibly a decade or more. The universe does not give up its secrets quickly, and the scientific community does not claim them before they are ready to be claimed. But the trajectory is clear. We are in the opening chapters of the age of atmospheric biosignature science. We have built the instrument, we have identified the target, we have collected the first data and found something that demands follow-up. The follow-up is coming. It is funded, planned, in progress. And while it proceeds, while the telescopes observe and the data accumulates, and the statisticians run their models and the reviewers sharpen their critiques, we have to live in the in-between. We have to carry the knowledge that there is a planet 120 light-years away whose atmospheric data contains a molecule that, on Earth, means life, and that we cannot yet say with certainty whether it means the same thing there. We have to hold that possibility. We have to be careful with it. Careful not to collapse it prematurely into certainty in either direction, not to announce a discovery that has not yet been confirmed, and not to dismiss a signal that has not yet been explained away. We have to sit with the most consequential maybe in human history, and wait for the universe to tell us which way it resolves. This is one of the hardest things science asks of the people who follow it. Not the math, not the instrumentation, the patience, the willingness to hold an open question open, to resist the cognitive pressure to resolve ambiguity prematurely, to live in uncertainty without letting it become either despair or false hope. Because what is at stake, if the signal is real, is not just a scientific result. It is not just a line in a paper or a point on a graph. It is the end of cosmic loneliness. There is a weight to cosmic loneliness that is hard to name because it is so pervasive and so long-standing that it functions as a kind of background condition of human existence. We have never known anything different. Every civilization in human history, every culture, every religion, every philosophy has operated under the assumption that Earth is the only living world, that the universe, for all its vastness, is ours and ours alone. This assumption is so embedded that most people carry it unconsciously. They do not think of themselves as cosmically lonely because they have never had the experience of not being cosmically lonely. It is like asking someone who has lived their entire life at altitude what it would feel like to breathe sea-level air. They cannot know what they are missing because they have only ever known one condition. The confirmation of life on K218b would not be the delivery of alien intelligence to Earth's doorstep. No one is coming. No message will arrive. No relationship of any kind will form between us and whatever organisms inhabit that ocean. The distance is too great, the biology too foreign, the communication too impossible. But the knowledge, just the knowledge, that there is another world where chemistry has organized itself into something that lives, changes the background condition of human existence in ways that are difficult to fully articulate but deeply, viscerally real. You would go to sleep knowing that out there, 120 light years away, something is alive. Something is metabolizing and dividing and drifting through an alien ocean under a red sun. Something that has been alive for perhaps billions of years longer than any life on Earth. Something utterly foreign, and yet in the most fundamental possible sense, family. Built from the same periodic table, subject to the same thermodynamic laws, participating in the same ancient cosmic process of life, organizing matter against entropy. That knowledge does not give you neighbors, but it gives you something almost as profound: context. It tells you that life is not an anomaly, but a pattern, that the universe does not grudgingly permit life in a few rare exceptions. It produces it, wherever the conditions are right, as a natural consequence of chemistry and time and energy. And if life is a pattern rather than an exception, then the question of purpose, of whether human existence has any meaning beyond what we assign to it locally, on this one small rock, takes on a different shape. Not a bigger shape, not necessarily a more comfortable shape, but a different one. We are not the sole experiment. We are one instance of a recurring phenomenon, a phenomenon that stretches across the galaxy, that has been happening for billions of years, that will continue happening long after this particular instance of it. Us, humanity, the civilization that built James Webb, has ended. There is something in that realization that is simultaneously humbling and exhilarating. Humbling because it removes our special status as the only living thing in an empty cosmos. Exhilarating because it suggests that the process that produced us, that has produced consciousness and curiosity, and the ability to ask questions about the universe we inhabit, is not unique to Earth. If life is common, then complexity may be common. If complexity is common, then the evolutionary pressures that produce intelligence, the advantage of modelling the world accurately, of predicting the future, of cooperating with others, of solving problems, may operate on other worlds too, not inevitably, not everywhere, but somewhere. Somewhere in the galaxy, perhaps right now, perhaps on a world we have not yet found. There may be a mind looking up at its own sky and asking its own version of the question we have been asking for thousands of years. Are we alone? If K218b is alive, the tentative answer is no. Not in the way we imagined. Not with the signal and the handshake and the confirmation that another consciousness is out there. But in the quieter, more fundamental way. The way that says the universe is alive, genuinely, not just here but there. Not just in one place but in pattern. Not just by accident but by some deep tendency of chemistry and physics that we are only beginning to understand. That is not nothing. That is everything. If the signal is real, If K2-18b is alive, then we are the first members of our species to know it. That is not a metaphor. That is literally true. The researchers who published the 2023 paper, the scientists reading it, and everyone who has followed this story since are existing in the first moments of a new kind of human awareness. An awareness that the universe contains living worlds beyond our own. And awareness, in the human tradition, creates obligation. There is an obligation to keep looking, to fund the telescopes, to build the next generation of instruments, to ensure that the question being asked of K2-18b gets asked of hundreds of other candidate worlds, because if life is there, it is probably also elsewhere, and the full picture of how common it is requires more than one data point, even a second one. There is an obligation to be honest about what we know and what we don't. The history of premature scientific announcements and premature dismissals in the search for extraterrestrial life has not served the public or the science well, yet the careful, precise language of the Cambridge team's paper is a model for how to hold this discovery, firmly enough to take it seriously, loosely enough to allow the evidence to evolve. There is an obligation to think about what we would do if the signal is confirmed, not immediately, not politically or diplomatically. There is no diplomatic relationship to be established with phytoplankton 120 light-years away, but scientifically. What would a confirmed second biosphere change about our models of habitability, of planetary science, of the distribution of life in the galaxy, of the conditions necessary for the emergence of biological complexity? These are not idle questions. They are the foundation of the science that would follow confirmation, and the preparation for that science, the theoretical frameworks, the observational programs, the interpretive tools, needs to be built now while the confirmation is still pending, so that we are ready to use it when it arrives. And there is an obligation that is harder to name, an obligation to pay attention, to actually reckon with the possibility that is in front of us, rather than absorbing it as another piece of news and moving on. The universe may have just offered us the most important piece of information in our history. The possibility that we are not alone. The possibility that life is not unique to this pale blue dot we have spent our entire existence on. That deserves more than a headline. It deserves sustained, careful, humble attention. It deserves exactly what you're doing right now. Epilogue. The world that was already there. When James Webb turned its golden mirror toward the constellation Leo and collected the photons of K2-18b's filtered starlight, it was performing the most precise measurement in the history of astronomy on a world that had been there, orbiting its dim red star for billions of years before any human looked at the sky. K2-18b did not become interesting when we discovered it. It did not become significant when we published data about it. It was there, alive, perhaps, drifting in its ocean under its red sun, long before our solar system formed. Long before the molecular cloud that would eventually collapse into our sun had begun its first gravitational contraction. Long before Earth, long before oceans, long before the first self-replicating molecule in our own warm, shallow seas decided, against all thermodynamic probability, to copy itself. The organisms of K2-18b, if they exist, have been living in their ocean for longer than life has existed on Earth. They have evolved, adapted, lived, and died in their alien chemistry for spans of time that dwarf our entire biological history. They are not newer than us. They are not waiting for us. They are not aware of us. They are simply there, as they have always been, as they may always be, long after we are gone. The universe did not begin when we arrived in it. It was already full of itself, already ancient, already vast, already possibly teeming with the quiet, unremarkable persistence of life in forms we would not recognize. We were the last to know. And perhaps that is the most important thing the James Webb Space Telescope has given us. Not a discovery exactly, not even a confirmation, but a moment of catching up, a moment of finally having instruments sensitive enough to ask the question seriously, and a universe ancient enough to have been doing the thing we were looking for, quietly, the whole time. The sky you look at tonight is the same sky it has always been. The same stars, the same darkness, the same distances that have humbled every human mind that has tried to grasp them. But somewhere in that sky, 120 light-years away, in a direction you can find, in a constellation you can name. There is a world that may be alive, a world whose light is arriving here, now, carrying its chemical fingerprints, waiting to be read. It is not close enough to visit, not familiar enough to feel like home, not near enough in time to tell us what it looks like right now. But it is there. And if it is alive, if the signal holds, if the data confirms, if the interpretation survives the scrutiny of the years ahead, then it has always been there, alive and metabolizing and exhaling its quiet chemical whisper into a universe that was listening. We just finally built an ear good enough to hear it, built an ear